Day 2 of integration by substitution, we'll look at more complicated integration by substitution, as well as some definite integrals that use integration by substitution. Number 11, if we look at the integral of x times the square root of 1 minus x, if we make u equal to x, that does us no good. But if we make u equal to 1 minus x, then I can replace the 1 minus x underneath the square root with the square root of u. The issue with this is I still have an x over here. So if I have du equals negative dx, basically what ends up happening is I have this dx gets replaced by a negative du, so I have negative the integral of x root u du. I can't integrate with an x and a u in the same problem. However, if I notice that u equals 1 minus x, I can rearrange things to make x equal 1 minus u by adding x and subtracting u from both sides. What I end up with is I end up with being able to substitute 1 minus u in where x was. Now everything's in terms of u's, and it's also way easier to integrate, because if I have the integral of x times root 1 minus x, that's pretty awful. But if I have negative integral of, I'm going to rewrite this as u to the 1/2, just as I'm thinking about it. So when I have root u, I can end up with root u distributing in, and this becomes u to the 1/2 minus u to the 3/2, and this is so much easier to integrate. So when I continue to do this problem, I end up with negative, and then I do an integral here. So the integral of u to the 1/2 is 2/3 u to the 3/2, and the integral of u to the 3/2 is 2/5 u to the 5/2. And then we have this plus c. So I can write my final answer by replacing u with 1 minus x. So I have negative 2/3 1 minus x to the 3/2 plus, notice it turned into a plus because I'm distributing the negative sign, plus 2/5. I don't want to put a u in because I'm writing my final answer. So this is going to be 1 minus x to the 5/2 plus c. Number 12. So if I look at this problem, I can't just take the, well, I mean, I technically could, but I'm going to kind of leave it like this for right now. So I have the integral of x plus 3 over x minus 1 dx. If I make x minus 1 equal to u, what I now have is the integral of u, and then I can just make a straight substitution dx for du. Now I still have this x plus 3 in the numerator, and I'm not allowed to deal with this. However, if I notice that u equals x minus 1 means that x equals u plus 1, I can replace the x in the numerator with u plus 1. So now I have the integral of u plus 1 plus 3 over u, and I can make that the integral of u plus 4 over u. And I can continue to simplify this. Notice that if I have a monomial in the denominator, I can rewrite this as u over u plus 4 over u. So that becomes 1 plus 4 over u du. Now I integrate this. The integral of 1 is u. The integral of 4 over u is 4 times the natural log of the absolute value of u plus c. And now I can substitute x minus 1 in where u was. So I have x minus 1 plus 4 natural log of the absolute value of x minus 1 plus c. And that's how I do number 12. One other thing that you could have done if you wanted was you could have separated the x plus 3 into two separate terms. So you could have made this the integral of x over x minus 1 plus the integral of 3 over x minus 1 and done it separately. There are some problems where you're going to have to do that, but in this particular problem, that doesn't actually make anything easier. It actually probably makes it a little bit longer. All right, let's take a look at problem 13. There's a lot of complicated stuff. Again, if I just make u equal to x, that won't do anything. So I'm probably going to have to choose one of these terms with the natural log of x in it. So I'll choose the one that's squared. So 3 plus the natural log of x equals u. So du, the 3 is a constant. Natural log of x is 1 over x when I take the derivative. And then I have dx. So if I want to replace dx with du, I would replace it with another x term in there. So let's just kind of replace what I have and see what I got left. So 3 plus x, or 3 plus the natural log of x became u. I still have this natural log of x minus 4 floating around that I'm going to have to get rid of. I have a 2 in the denominator. I'll move that to the outside. Then I had an x. Now notice that I'm going to replace dx with x du. So this is good. The x's cancel, which is nice because I had a natural log of x in the numerator and the denominator. So that kind of worked out pretty well. Now notice that I still have this ln of x in here. So I'm going to take what I have with 3 plus natural log of x equals u. I'm going to make natural log of x equal to u minus 3. So I'm going to replace this natural log of x with a u minus 3. So I have 1/2 integral of u squared times u minus 3 minus 4. I don't need to put a denominator in there because the x is canceled. And now I have this du going on. So I'm going to continue to simplify. This minus 3 minus 4 is really just minus 7. So I end up with 1/2 times the integral of u cubed minus 7u squared after I distribute that in. And so now I take the integral of this, so I have 1/2 times 1/4 u to the 4th minus 7/3 u cubed plus c, and now I just have to replace the u's with 3 plus natural log of x. So I have 1/8 when I distribute the 1/2 and the 1/4. So I have 1/8, 3 plus natural log of x to the 4th minus 7/6, 3 plus natural log of x to the 3rd plus c. So we're going to do definite integration when we have to use substitution. I'm going to show you two different methods for this. Notice that in 14 and 15, I'm using problems that we did yesterday, so that'll save us a little bit of time. So when we integrate 14, we get 1/4 tangent 2x plus 7, the quantity squared. Now, when we do definite integration, obviously we don't need the bounds on c, or the plus c there. So one way to do this is called with resubstitution or back substitution. You might see this on the internet. So if we use back substitution or resubstitution, basically what we do is we integrate with u's. We essentially turn this into an indefinite integral. So secant squared 2x times tangent 2x plus 7 dx. We essentially turn it into an indefinite integral, make use substitutions, substitute everything in, and then we end up with this integral, so on and so forth, equals 1/4 u squared, and then we replace the u back. And so then once we get this 1/4 tangent squared, or tangent 2x plus 7 squared, we then go from negative pi over 8 to pi over 8. So we basically treat it like an indefinite integral. And then when we're done, after we substitute the u back in, then or after we substitute tangent 2x plus 7 back in, now we plug in pi over 8 and negative pi over 8. So in that case, we would have 1/4 times tangent of pi over 4 plus 7 squared minus 1/4 tangent of negative pi fourths plus 7, the quantity squared. So we're substituting these values for x back in for x, and we figure out what happens. So this is 1/4 times tangent of pi over 4 is 1. So 1/4 8 squared minus 1/4 tangent of negative pi fourths is -1. So this is 6 squared. We end up with 64 over 4, which is 16. We end up with 36 over 4, which is 9. 16 minus 9 equals 7. So this definite integral, we would get 7. The other way of doing this is by changing the bounds. So instead of treating it like an indefinite integral, integrating, substituting the x part back in, and then treating it like it was a definite integral all along with negative pi over 8 and pi eighths, what we could end up doing is when we make the u substitution, and remember the integral for this was I'm sorry, not u squared. The integral was u du, and we had a 1/2 on the outside. If you don't remember, check the backside of your notes. Instead of just treating it like everything is an indefinite integral, we can remember that u in this problem was tangent 2x plus 7. And so I'm going to make the bounds now in terms of u. So if I make the bounds in terms of u, what I can do is I can take the negative pi over 8 and the pi over 8 that we had, and I'm going to substitute them in this equation and figure out what u would be if x was negative pi over 8 and what u would be if x is pi over 8. So I'm going to take negative pi eighths, substitute it in, tangent of negative pi fourths plus 7. That gives me 6. So when x is negative pi fourths, u is 6. When x is negative pi eighths, u is 6. When I substitute in pi eighths, I get tangent of pi over 4 plus 7. So when x is pi eighths, u is 8. So instead of having the bounds from negative pi over 8 to pi over 8, I have the bounds from 6 to 8. So in this case, I'm changing the bounds. Essentially, these two things do the same thing. One is taking the negative pi eighths and pi eighths and substituting it in at the beginning. The other one is taking the negative pi eighths and pi eighths and substituting it in at the end. Sometimes there's a multiple choice question on the AP test where your u substitution, they ask you to change the bounds. But other times you can just choose which method you like best. So in this case, I will integrate u du from 6 to 8. So I have 1/2 times 1/2 u squared, and I'm going to sub in 8 and 6. So I have 1/4 8 squared minus 1/4 6 squared. And notice that that gives me the exact same thing I had over here. So really, they're not any different. It's just kind of a difference in opinion as to how to do it. Number 15, remember our u was 2x minus 5 in that problem. And so I had 1/10 2x minus 5 to the 5th as what I got when I actually integrated. So the first way of doing this problem is subbing in u, doing all the integration like it's an indefinite integral. I get 1/10 2x minus 5 to the 5th as my answer. And then I go back and I treat it now like it is a definite integral and sub in 3.5 for x and 2 for x and kind of see what happens. So I get 1/10 times 7 minus 5, which is 2 to the 5th, minus 1/10. 4 minus 5 is -1 to the 5th. So I end up with 32/10 plus 1/10, and I get 33/10 or 3.3 as my answer. If I did this with, so that was with back substitution or resubstitution. If I do this with changing the bounds, so I can do the integral of u to the 4th du, and remember that when I make the du substitution back in that problem, I had a 1/2 on the outside. So now what I can do is I can change the bounds and figure out what goes in these spots. So if I want to figure out what goes in these spots, I take what my original bounds were in terms of x, and I sub them in to u equals 2x minus 5. So u equals 2 times 2 minus 5, and u equals 2 times 3.5 minus 5. So in this case, u ranges from -1 to 2. So instead of the bounds being from 2 to 3.5, if everything was in terms of x, the bounds are now from -1 to 2. So if I integrate this problem, I get 1/5 times 1/2 u to the 5th, and I evaluate from -1 to 2. So notice the 1/2 and 1/5 becomes 1/10, and then this u to the 5th, I substitute in 2 minus 1/10. What happens when I substitute in -1? And notice I get the same thing that I did if I did back substitution. So it just kind of depends on what you want.